Hello, everyone. Welcome to this new edition of the IMPACTIVE webinars. We're here again to talk to one of our partners in the project. We had a fantastic series, including some of our sister projects funded by the European Commission. But today we're centered in IMPACTIVE again. IMPACTIVE, a project that's developing new mechanochemical solutions for greener pharmaceuticals. So we're doing a series of different webinars with different partners because IMPACTIVE is a consortium with a lot of partners all over Europe. I was going to say the number, but I don't want to make up the figures. Go to our webpage, mechanochemistry.eu, to find more information and get all the details. And don't forget to subscribe to our newsletter to get the latest news about the project, and then also important information and dates about webinars like this one, with very cool developments in research related to mechanochemistry.
Good afternoon, Fernando. Good afternoon, everyone. And thank you so much for the introduction and for the invitation. As you know, today I'll be talking about scale-up and how we approached it within the IMPACTIVE project. So let's start with this talk titled From Lab to Plant, Scaling Innovation. First, I'd like to tell you a little bit about DesSolutio, the company I represent, and when I work as an assistant researcher. DesSolutio is a company based in Portugal, more precisely in Caparica, near Lisbon. We are a spin-off of the Nova School of Science and Technology. And we are founded by Alexander Paiva and Rita Duarte, who act as our CEO and CSO respectively. Our main work at DesSolutio focuses on the production and industrial application of NADIS, which stands for Natural Deep Eutectic Systems. For those who might not know them, NADIS are a fascinating class of clean solvents, and they are made of natural compounds like amino acids, sugars, or organic acids. And what makes them so special for industry is that they break down naturally, they are practically non-toxic, and we can design them for specific tasks. Working with NADIS has trained our team at DesSolutio to think differently. We try to move away from the traditional harsh solvent rules, and we design cleaner, more sustainable processes from day one. And this leads me to our specific role in Impactive. To do that, I would like to show you this image. Usually, when people think about the pharma sector, they picture this: test tubes, glass flasks, and so on. And while this is a crucial part of R&D, the actual manufacturing industry looks much more like this: a facility filled with steel tanks, large reactors, and heavy equipment. Most of the time, these two worlds are separated. They share the same goal, but they often operate like isolated islands. Our role in Impactive is to be the bridge to bring these two sides together. We take the brilliant science and innovations that happens in those lab spaces and engineer it into a viable product that brings real value to society and can be successfully sold in the market, which is what really happens in the industrial world. Having said that, let me show you a simple concept to help us understand the real problem of scale-up. When working in the lab, we handle volumes of around 100 milliliters, like this first cube. When we get good results from a test, we might think about just multiplying the volume, let's say taking it to 1 liter, which is still easy to handle in the lab. Following this logic, we could increase to even larger volumes, such 1000 liters, bringing us into the scale of pilot plants. But looking at these images, it's easy to think that we could scale up perfectly just by multiplying everything by a number. But the reality is quite different. If we look at the surface to volume ratio, we realize that as the volume grows, the available surface area drops very fast. This is the exact problem that engineers must solve. Having less area means we must build highly efficient heating or cooling systems to copy the exact conditions we had in the laboratory. In the lab, you had plenty of surface area. To heat or cool, you just move the flask to the heater or leave it in the bench. But in the real plant, moving heat in and out is a massive engineering challenge, and if we fail, it becomes a major bottleneck. The same goes for mixing. Stirring in the lab often just means dropping a small magnetic bar into a glass. But in industry, we have to design custom mixers with specific blades and baffles inside the tank. We must find the perfect flow and shear rate so the whole tank mixes perfectly. What I'm trying to say is that this physical limit is the exact point where we transition from lab science into a real engineered product. With this concept in mind, we can move on to the actual work we do in Impactive to scale up a process. But a quick note before we continue. From this slide onward, you might notice some blurred text. This is not a connection issue. This is done on purpose to respect our non-disclosure agreements regarding sensitive data. So let's take a look at the following procedure. What we see here is an excellent result from our research team. It is the final product of many different tests and long hours in the lab until they found a solid and repeatable method designed to give very high conversion rates. However, when an engineer reads this is usually what happens. What we have here is a translation problem. The lab work is fantastic, but through an industrial lens, a whole new set of questions pops up. This is exactly where the solution steps in as the bridge I talked about before. We had to translate the technical language of the lab, which focuses on the chemical reactions, into the technical language of the industry, which is driven by cycle times, flows streams, utilities, and cost. Let's be clear on this. Our goal here is not to criticize, but to co-create. The first step in scaling this discovery is understanding it. We asked the research team about all the hidden details that they might have not written down simply because their main focus was the yield and not the industrial design. At this stage, as scale-up engineers, our job is to ask questions and dig deeper. This team workspace is where we gather golden information about potential equipment or specific properties. We can even ask for the missing lab data whenever is possible. This is also where we suggest ideas that could really lower the cost of the process. To put this work into perspective, let me give you a concrete example relevant to the innovations we see in Impactive. In the lab, a chemist might successfully make the product in a 50 milliliter jar. But when we scale that up, for example, to an industrial ball mill, the engineering analysis completely changes. We are no longer just at the chemistry, we are looking at at the mechanics too. This is where talking with the researchers becomes absolutely critical. For example, during our deep analysis of the chemical we use, we might notice that a specific reactant is using a large excess. When we ask why, we often find out that the excess is not needed for the chemical balance. It is just there to help the powder mix better or prevent it from sticking. It is helping the physics, but not the chemistry. By working together, we might find a mechanical solution to improve that mixing instead, allowing us to drastically cut the amount of that reactant. This single change can reduce the required equipment size, lower the amount of power needed, and completely transform the cost of the entire process. And this teamwork goes far beyond the reactor. It extends to the downstream process too. Lab work usually purifies the products very fast, but in the industry, we must design buffer tanks, industrial filters, and extractions, among others. This requires a whole new set of data. We have to evaluate a lot of properties like properties, porosity, and drying times, as well as the rheology of the fluid. We also build recycling loops to minimize waste and water use. This engineer work is exactly what makes the plant economically and environmentally viable. And once we are sure about the chemical procedure, we are ready to move into a space that is much more familiar to the engineering. In the Impacted project, we applied an Industry 4.0 strategy for two main reasons. First, as we are designing completely new processes, we have no historical data to guide us. And because we must test many different options, it's simply too expensive to build a real pilot plant for each one. It will waste too much money and material. And second, we must prove with strict technical data that these processes will work in the real world and are worth the investment in detailed engineering. So this is why using computer models adds so much value to our design. We start by writing the mathematical models that explain what is happening in the process, and then we build chemical equations that control the core reaction, while we have a whole other set of equations related to the purification steps of the plant. All of this is checked through rigorous mass and energy balances. We evaluate whether these equations are truly solid by running multiple tests and iterations. Doing this step right is crucial because it makes our final design highly reliable. And all this previous effort, agreeing on the information, building models, asking questions, and checking data, give us the precise inputs we need to feed into our virtual pilot plant. And now we reach the part everybody pictures when we talk about scale-up, Aspen and process simulation. But let me be clear, Aspen is an incredible tool, but as you just saw, it takes a huge amount of prep work before we even open the software. At this stage, we draw different flow sheets and we compare the pros and cons of different ideas. Then we build simulations to test them. But why do we simulate? Well, because this program gives us a safe space to test ideas without spending money. They feature highly complex thermodynamic models and databases, making our calculations far more precise. However, simulating new pharma processes brings a major challenge. These molecules are so new, they simply don't exist in any standard database. And Aspen is not magic. If it doesn't know the molecule, it cannot run the math. So how do we solve this at DesSolutio? We use advanced predictive models to break the molecule down into its functional groups in order to estimate all the missing data like vapor pressure or critical temperature. Thanks to this heavy lifting, when our virtual pilot plants run different operations like an extraction or a distillation, the physics are backed by real science and not just blind guesses. But let's keep in mind that our main goal when we run calculations in Aspen is to validate the design and give it absolute precision through continuous work. As a result, we obtain data that allow us to define the equipment, their dimensions, materials and constructions, and cost. We also calculate other critical metrics such as the required energy demand and the necessary plant utilities. The design includes safety rules, and we also size other essential plant systems such as clean-in-place washing cycles, while keeping in mind the limits of the equipment itself. And at this point, many might say that the scale-up is finished, but in reality, what we have right now are just ideas and a list of equipment. This is not a final process yet. To truly achieve scale-up, we must deliver a plan that can show the project stakeholders that this process can be profitably built in a plant. So the next steps for our virtual plant is to give it industrial order, or what I like to call industrial choreography. To do this, we look at the processing times and when each machine is used. This allows us to map out the critical path of the process and deeply understand the limits of each unit. By doing so, we avoid duplicity of equipment and we find process bottlenecks, idle times, and the support tasks needed to keep the plant running. Once the data process schedule is built, calculating both CAPEX and OPEX becomes much more straightforward and accurate. Finally, with all this work done, we generate a complete report as our main deliverable. This package details the required equipment, the technical specifications, the stage where they are used, quantities, costs, and the consumption of utilities. It also contains the stream summaries and the calculations of key indicators to compare this process against other options. An important part of our job in IMPACTIVE is acting as an early green filter. Before our partners do the official life cycle assessment, we run a pre-calculation directly from our simulations. We look at basic math metric like the PMI, which tells us exactly how many kilograms of materials and water we need to make just 1 kilo of the drug, and check what it says. If a virtual plant shows a terrible PMI, we know the design isn't good enough. We go back, redesign the flowsheet, and simulate again until we bring that number down. We have to have in mind that we aren't just optimizing for cost, we are optimizing for the planet too. This screening allows us to hand over a clean inventory so the LCA team in Work Package 6 can focus their deep environmental analysis only in the absolute best candidates. As a brief summary, DesSolutio, acting as part of Work Package 5, takes the data from other work packages as our inputs. We analyze them, integrate the necessary physical properties, and develop the process step by step alongside our virtual pilot plant simulation. These results are used to size the equipment and create precise production schedules. The final report on the most promising processes is then handed over to the next working groups. They will further increase the technical rigor by providing the technology's green impact through life cycle assessments. In essence, as part of Work Package 5, our role is not just to draw flow sheets. Our job is to provide engineering certainty to the brilliant innovation discovered in the lab. Thank you so much for your time and your attention.
Thank you so much for the very kind and very nice presentation. It was very interesting to learn more about the objectives that you follow in DesSolutio within Impactive. I'm gonna wait a bit till we get questions from the audience. So If you're watching this on YouTube, please go into the chat and then input your questions in text, and then we'll review them and hopefully pass them over here. And if you have any other follow-up questions, maybe just direct them to us through the webpage and our social media, and we can address them later. But just before we go to the audience questions, I've got a couple of my own. Because one of the things that you've gone through is like the types of programming software that you use, and I know that mechanochemistry is quite a new. I know it's not new, but it's sort of new in terms of research and applications in industry now. So there's probably not a lot of existing software that you can use to develop this type of solution. So what do you use exactly, and how does it compare to modeling other type of reactions that already have been developed in the chemistry space? Is mechanochemistry special, and what makes it special in terms of software and simulation?
Well, to be completely honest, one of the thing is that you don't have a specific software for mechanochemistry. So, in order to scale up processes that are meant to be done by mechanochemistry, we have to take a different approach. Normally, when you work with Aspen, for example, for simulations, you have the most of the things you need in that software. But in this case, where the software really shines is in the downstream process. But in the case of mechanochemistry synthesis, what we do is to change the approach. We don't try to simulate the physics inside the software. What we do is to work directly with the research team and utilize their data like kinetics and energy data and construct, and we build a block in the software as a main reactor. Where the software really shines is in the downstream, where we got all the data to optimize that very important part of the process.
Yeah, thank you so much. That's very interesting answer. I was also wondering, you were talking about data and how you use it to model the different mechanochemical reactions. What would you say is the most important parameter in terms of modeling the scale up? Because obviously, in mechanochemistry, there's going to be a lot of important factors, and one of them could even be the change of machinery altogether, because the ball mills that you use in the lab may not be the same equipment that you use industrially, because you may have like resonant acoustic mixers or twin screws extrusion and other mechanisms. So what's the most important parameter? And then also, how do you translate small ball mills to big extruders industrially? Is that a challenge that you normally face?
Oof, that's a great question. Scaling up is all about the right balance. So for, our goal here is design a process that is green, but is also financially viable. So maybe in thinking it in a engineering point of view, I can highlight three important points to highlight as challenges. The first is the heat transfer, as I explained in the presentation, because in a laboratory, this is something you don't take in account unless you need a specific temperature, but it's easy to achieve. In the industry, is one of the hardest problems you have to solve, both for auxiliary systems and for the design of the equipment. The second thing I think is mixing, because working with thick fluids and slurries or dry powders, like in mechanochemistry, requires huge motors and special designs of the equipment in order to make them function properly. So this in a small flask is not a problem, but in the industry is a challenge, a very important challenge to overcome. Ultimately, I think the last thing I can highlight is the separation, the product separation, because in the industry, the downstream, where you have to design processes like drying, filtering, or even a crystallization, requires a very accurate control and design in order to be economically viable and to generate the less waste possible. That is one of our main goals here. So I think that are the three pillars I can highlight from the challenges. And according to your question about the design of the equipment, uh, it's true it's not easy to upscale a tiny ball mill from a large one or to replace it with a RAM, for example. But the reality here is that as engineers, we have a set of models that we can use that are very robust in industrial scale. And working with these models plus suspend plus the data we have from the laboratory, we can interpolate that and have very accurate results when we scale up, for example, a larger equipment like a ball. The challenge here is to scale up properly and to calculate the right power demand of that equipment, as well as to keeping in mind the materials and special conditions this equipment has to have in order to work with this kind of reactants.
Thank you so much for the answers. We actually have two questions from the audience, so I'm gonna sort of skip my list of questions and go back to the questions that have come from the people watching live on YouTube. Um, so I think it was towards the end of the presentation, you had a graphic showing how you get information from some web packages, which are the different teams within Impactive, and then you feed to another work package who's doing more of the LCA and sustainability analysis. But the question is actually, do the arrows go back as well? Like, does your information from simulations and calculations go back to WP2, work package 2, work package 3 and 4, so they can actually go back to the lab and experiment with the new data that you provide after your calculations? Is that a relationship that happens within the project as well?
Nice question. Yeah, just only to mention it, the arrows were meant to get easier the comprehension of what was explained. But yes, we have back and forward information. I think that is one of the most powerful tools you have in a very diverse work team as we have in Impactive. Uh, as you know, in the presentation, I talk about co-creation. I put that in the first step of what we're doing, but that happens all the time because as you are working with all the scale-up processes, the other work packages are working as well, and they are very good professionals and very hardworking people. So I can't complain about that. So as they are advancing with new discoveries and optimizations, this information could change the work I am doing and the work I am currently doing could get ideas to them. In my opinion, this kind of this moment in the work is the worthiest one because a very good ideas came after those discussions. Uh, we have meetings all the time in order to catch up with everyone's work And in that moments is when these arrows came back and forward.
Yeah, that's a very nice answer. And actually, you mentioned a couple of things that came up in the next question that we have from the audience without having read it, which is pretty amazing because you mentioned co-creation and collaboration. And the next question that we have actually looks into co-creation, and in particular, working sort of in the interface between chemistry and engineering. Um, I'm assuming that, it's almost like what we face in Agatha between scientists and the public doing communication. But for you, it's like, how do you fight and how do you sort of mediate those fights between the chemists and the engineers when they're both defending their own perspectives? They both, you know, consider different parameters as the key, but then obviously as the sort of person in between, you need to decide, okay, this parameter may be good for the small scale, but it's not good for the big scale. This product is not very good for co-crystallization in big scales because it's too toxic. How do you mediate between the chemists and the engineers? And also how do you adapt the language from talking to people that have like tiny flasks and maybe, 200-gram reactions to people that have kilos and kilos and tons of pharmaceuticals? How do you deal with this type of conversations?
Well, okay, as I said, I think the two key words here are co-creation and translation. Because, Fernando, this is good because we can talk about something that is not so engineering, but the reality is in every organization, the only thing our organization has in common is that they have humans involved. So the reality is, even we are engineers, PhDs, accountants, etc., we are all humans, and all the things are reduced to these relations you create with your coworkers. In my case, I had the experience to work with a lot of different professionals, and I understand that sometimes uh, people uh, hasn't got an ego problem. The problem is that they are focused in their work and they don't know the work you are doing or how to do it or what are you doing. So when I talk about co-creation, this is the first you have to do, to talk with people, to talk and try to understand their language. For example, now we are both speaking English, and obviously we have different words in our dictionary, but we managed to understand each other. That's the idea. With a chemist, with an engineer. Obviously, the mind of an engineer is set to an industry to get a product and to get income of that product. The mind of a researcher, in this case a chemist, is set to have a high yield in the laboratory. None of them is wrong. They both are right. I think the goal in here, the goal you can dig here is the point in the middle when these both work can understand each other. That's why I focus on the speech when I took the data from others to do my job, because the innovation really happens in those lab spaces. What we do is to give it industrial value so the people who understand other languages, like ROI, for example, can see that innovation. I don't know if I explained it properly, but that's the idea.
I think you explained it very well. And yeah, we actually have another question from the public, which like when we talked off camera, we mentioned briefly that sometimes questions from the public get very specific. So feel free to maybe answer in private afterwards, because this one sort of goes back to something that I asked at the beginning. and someone's asking, is there a specific simulation software that we can use in mechanochemistry? I'm assuming it's a very generic question in the sense that they're not specifying whether it's for LCA or modeling mechanochemical reactions for the lab or modeling scale up. But I'm assuming, like, chemists use Gaussian for, like, modeling small molecules. Is there anything as international as that for simulating stuff in mechanochemistry?
No, I can answer that question. As I know, there is not a commercial generic software that models mechanochemistry. Most of the softwares, like Aspen, are focuses on fluids, and they do a very good job in that field. The thing with mechanochemistry is that it's an area of investigation, of development that is very promising, but we have a lot to learn about that. So, as it's not so used, in my opinion, as not so used as other uh, classical approaches, there isn't already the need to develop that kind of software. But even develop that software will be very hard because in the case of mechanochemistry, I don't want to be very technical in this, but in the case of mechanochemistry, the kinetics and other important properties uh, have a different approach from the classic chemistry we know. So that's why these groups of researchers are working so hard to understand it. And it's a very interesting field to study because it allows you to achieve some reaction and some conversions that in the classical approach uh, are impossible. But okay, I want to do a very long answer, but to be short, there isn't a software to do that. The idea, the approach we use is to work with all this information we have from brand new uh, research that the Work Package 2, for example, has has done, and we design our own models to fit a software like Aspen. In
Mhm.
our speed, we have very accurate result with this approach. So this is cheaper than develop, for example, a specific software for that.
Thanks. That was a very comprehensive answer, and I think very clear as well. I like to put a positive spin on things. Maybe it's a great opportunity to develop a specific software as a sort of spin-off of Impactive. But that sounds complicated from what
Well,
you just said. So yeah, I
well,
think
you know where to find me.
oh yeah. If you want to start the programming and create a GitHub project and then get started, yeah, that could be a great idea. Maybe we could get some more European funding for that. But again, we don't have any more questions from the audience at the moment. But so I wanted to sort of close now. To keep it sort of brief in the sense that people will rewatch this and go back to your presentation and maybe send you some questions. I want to thank you again for your time, for a very nice presentation, Juan. It's been really really nice and interesting to learn about your work at DesSolutio, and I sort of want to just remind everybody that Impactive is a project funded by the European Commission, and it's been going on for like almost 3 years now, a bit over 3 years now. We still have a few months to go, so there's going to be more webinars coming up. There's going to be more content coming up on our webpage. It's mechanochemistry.eu. The webpage will probably outlive the project for a few years, so you're going to find information there if you're interested in mechanochemistry. And we're also putting together an educational platform if you're interested in that, and getting more access to resources on mechanochemistry. So please check that out. Go to mechanochemistry.eu for more information. Feel free to subscribe to all our different ways to stay in touch. We've got Twitter, we've got LinkedIn, we've got a newsletter, we've got the webpage. We've got these webinars. We're going to keep doing webinars with more of our partners in the project. Again, thank you so much, Juan, for the very nice presentation. And thank you, everybody, for watching. Like I said, this will stay on YouTube. So feel free to, check it at any other time, send the link to your colleagues, and go back to the presentation whenever it's best for you. Thank you, everyone, and hopefully see you in the next webinar. Stay tuned for that.